Hi, today's the beginning of chapter 4. We are skipping section 3.4, so we'll not cover that. That's not part of the course this semester since we missed about a week of classes. Today we'll cover section 4.1, but there are also some other ideas that need to be mentioned in the chapter 4 toolbox. So let me start out with this. One of the concepts is an even function. And an example of an even function is when you have x, your independent variable, raised to an even power, such as 4, or 2, like in a parabola. The graph of this function here is this U-shaped graph. It's almost like a parabola, but it's flatter around the x-axis there, around its vertex. Since the number multiplying x to the fourth is negative, this graph opens downward. So when you see an even exponent like that, you will have an even function. If you have an odd exponent, you'll have an odd function. An odd function will have a different shape where the two ends of the function, of course they never end, they run off to infinity, but these two branches of the functions go off in different directions. Notice in an even function, they're always going to go off in the same direction, either down or up. Here, you're always going to have one going up, one going down. Notice I chose to display a negative coefficient, again multiplying the odd exponent, which is in this case is 5. And because it's negative, we're going to come in from positive infinity in the y-axis and go off towards negative infinity on the y-axis. So that's an example of an odd function. Also in the toolbox, the concept of the root function is covered, and we talk about even and odd in terms of root functions. Here's a simple one which we've graphed before: y equals the square root of x. Now of course, as I've shown in the green ink here, when you don't see the index of your radical sign, it's understood to be 2. There's an invisible 2 there. So the square root of x looks like that. Notice that the domain starts at 0, including 0, and runs off to positive infinity. Since you cannot take the square root or the fourth root or the sixth root or any root of a negative number, any even root of a negative number, therefore your domain will be restricted like this. Of course, if you were to put a negative sign in front of that x there inside the radical sign, then things would be reversed, so keep that in mind. It's a different situation when you're talking about an odd root function. Here we're looking at the simplest one, y equals the cube root of x. So we have an odd index on our radical sign, it's 3. Notice in this case, the curve similarly goes like that. You'll see that it's actually a little flatter than its neighbor that we just looked at, y equals the square root of x. But notice that it runs off in the negative direction also, because you can take the cube root of a negative number and the fifth root of a negative number and the seventh root and so on and so forth of a negative number. So the domain is different. It's all reals in this example. All right, so there's some concepts that we'll be using as we move along here. Chapter 4 is more studies into functions. And section 4.1 deals with looking at the graphs of functions. Let's look at example 1. One of the things that can happen to functions, one of the transformations that can happen, is a shift. So in example 1, we're asked to graph a simple function f of x equals the absolute value of x, which we've done before, and then a variation on that function, g of x equals the absolute value of x plus 3. If I set up a table and pick some simple x values, of course my f of x column is just going to be the absolute value of these values. In other words, we're going to throw away any negative signs we encounter. And we plot the absolute value function f of x, and it looks like this. That familiar V-shaped curve that we've seen before. Now, if we go ahead and calculate the values for g, you see what's happening. We're just adding 3 each time. Every value we got here naturally gets increased by 3. And 2 plus 3 equals 5, 3 plus 3 equals 6. So if we plot those points, we land here, and here, and here, and here. And you see what happened? We get the same exact shape, but everything is shifted up 3. So we say there is a vertical shift of 3, positive 3. Now we've seen that type of phenomenon before. If you recall with parabolas, if we looked at y equals x squared, a simple parabola, and then we looked at y equals x squared plus 2, it would have been shifted up by 2. So we have seen this phenomenon before. Let's look at a different kind of shift. Look at example 2 on page 247, I believe that is. In this example, again, we're asked to graph the absolute value function. So we know it looks like that. This one's a little wobbly there, but you get the idea. Okay. Then we're also asked to graph g of x equals the quantity x minus 5, equals the absolute value of the quantity x minus 5, I should say. So here, we're subtracting a number from x inside the absolute value bars, which is different from what we just did in example 1. Let's see what kind of difference that makes. Alright, so we'll pick the usual suspects for x. And we get the usual results for f of x. And all those points are plotted on that curve we already have up there. What do we get for g of x? Well, first you're going to subtract 5 from this negative 3, so you get negative 8. The absolute value of negative 8 is positive 8. Then you're going to subtract that 5 from x equals negative 2, so you get a negative 7. Absolute value of negative 7 is positive 7. When we do with negative 1, right, it decreases by 1 again. We get down to 6. And then 5, 4, 3, 2. So if we keep going here, 4, 5, 6, 7, we'll get 1, 0, right? When we put 5 in there, we get absolute value of the quantity 5 minus 5, which is the absolute value of 0, which equals 0. And finally we turn it around here and start going up again. So you see what has happened. This entire chunk of y values has sort of been transplanted down to here. If we start plotting these points, well, suppose I just start with this one, 4, 0. I'm sorry, that's 0, 5. There's a point where we intercept the x-axis. Now, as we get further to the right and go to 6, that's 6. You see, I'm all sideways in my world here. I'm having trouble reading my table. As we go to 6, we get that big thick 1 there. As we go to 7, we go to 2. In the other direction, as we go back to 3, we get 1. Sorry, as we go to 4, we get 1. It's hard to read this from the side, I'm finding out. At 3, we get 2. Okay. And you see what's going on. You see the V shape right there. If we kept plotting points and graphing them, we'd get the shape of the absolute value function, but it's shifted over 5. It's shifted 5 in the positive direction. I'm subtracting that 5. So that means whatever number you subtract from x inside the absolute value bars is going to result in a shift to the right. Now if you were adding 5, you would have shifted to the left. But what we saw in this case was a shift to the right of 5 units. All right, let's look at example 3. In example 3, let's look again at the square root function. We looked at the graph of it a few minutes ago. Sort of looks like a parabola lying on its side, but half the parabola is gone. Wonder why that is. Okay. Now we're asked to compare the graph of this function to this function. This is a slightly more advanced example because not only am I adding a number to the outside of the radical expression, in this case I'm adding -4, I'm also adding a number inside the radical side. So this maybe should make things shift up, down, right? Outside the radical sign. But the number inside the radical sign, is it going to be like we saw with the absolute value function a moment ago? Is it going to cause a sideways shift, horizontal shift? Well, let's see. I set up my table. Of course, I can take all these usual suspects here, but notice that because I'm adding 3, I can also put negative values in there as far negative as -3. If I plug -3 in there, I get square root of 0 minus 4. So that's 0 minus 4, that's a -4. If I plug -2 in there, I get square root of -2 plus 3, so that's square root of 1, which gives me a 1, minus 4, that gives me a -3. If I put -1 in there, I get square root of 2 minus 4, and this approximately equals, I put the squiggly equal signs there, this approximately equals -2.6. At 0, I would get square root of 3 minus 4, which approximately equals -2.3. So if I plot these points, I'm going to get there's -3, -4. Then -2, -3. -1, -2.6. 0, -2.3. Do you see a similarity yet? Well, we could plot a few more points. 1, 2, 3. At 1, we put 1 in there, we get square root of 2 minus 4. So, I'm sorry, we put 1 in there, we get square root of 4, which is 2, minus 4 gives me the -2. And we get some messy numbers here that I don't want to mess around with. Let's plot this one at least. Over here, at x equals -1, we go up to -2. We can never go left of here, because we can't take the square root of a negative number and still be getting real numbers out of it. So we have a curve that goes like this, and what we're seeing is it's got the same curve as this one, sort of. I didn't draw a great picture of it. So this is f of x equals square root of x. This is g of x down here. So it's like we took this curve, the original f of x, and shifted it to the left 3 places. And then it also got shifted down 1, 2, 3, 4. At -4, is where this first value evaluates, right? When we plug x equals -3 in there, we get y equals -4. So the bottom of the curve is -4. It's like this thing, f of x, got shifted down 4. So shift to the left 3, -3, is our horizontal shift. The vertical shift is that number there. So the number being added on here, remember this is a plus -4 if we think of it as being added on, that number being added on is your shift up or down. This number being subtracted is your sideways horizontal shift. Okay, now you do it. Do problem number 7 on page 258. Page 258, number 7.